So, hello everyone. Today we're going to be covering the future of large language model pre-training is federated. Now, I think this topic is pretty interesting when you have a bit of context to understand why this is relevant and necessary and why it's probably going to be the future of pre-training LLMs in some capacity or another. So with that being said, I'm going to skip a bit ahead in the paper after we go through the abstract just to give that context. But I wanted to make sure you all were aware that there's more information that kind of underlies the importance of this paper. So with that being said, let's actually just start with the abstract. Generative pre-training large language models, or LLMs, have demonstrated impressive performance over a wide range of tasks thanks to the unprecedented amounts of data they have been trained on. As established scaling laws indicate, LLMs' future performance improvements depends on the amount of computing and data sources we can leverage for pre-training. So federated learning, which is covered extensively in this paper, has the potential to unleash the majority of the planet's data and computational resources, which are underutilized by the data center-focused training methodology of current LLM practice. Our work presents a robust, flexible, reproducible, federated learning approach that enables large-scale collaboration across institutions to train LLMs, which would mobilize more computational and data resources while matching or potentially exceeding centralized performance. And from there, we further show the effectiveness of federated training and how it scales with model size and preset, and present. Our approach for training a billion-scale federated LLM using limited resources, which will ultimately help data-rich actors become the protagonists of LLM pre-training instead of leaving the stage to compute-rich actors alone. Now, there's a lot of loaded history in that abstract that I want to go through right now by jumping ahead a bit in the paper. So why the move to decentralized pre-training is necessary for the open source community is really outlined towards the mitigation of LLM demands. So while methods exploiting pre-training weights are highly beneficial to the wider community, they do not resolve the bottleneck of training. So right now we're kind of in a paradigm where fine-tuning models has become fairly democratized and decentralized from centralized LLM labs, where you can take a LoRa or do some QLoRa type quantization, fine-tuning, and alignment that doesn't require a large data center or a GPU-rich environment to actually make significant beneficial changes to an LLM for your given use case. The issue with the current state of affairs is that this same level of democratization and distribution does not currently exist with LLMs in regards to pre-training. Now, as of right now, the community has been relying on the decisions made by actors who are capable of pre-training LLMs with regards to the structure and data that they use. And ultimately, as a result, we end up both benefiting and suffering the downstream consequences for such reliance. So when Meta releases a new model, or when Mistral releases a new model, or even Google releases a new Gemma model, to the open source community, we all benefit from that in the sense that we get a pre-trained model that we can modify to our discretion as members of the open source community. But we also suffer because they end up setting certain standards for how models can be modified and changed. We're relying strictly on the data that they are willing to provide us, the compute that they've already provided in advance to train up these models up to over 1 billion parameters. And ultimately, these are very capitally expensive procedures that prevent us from essentially doing the same on our end because of the lack of GPUs and compute needed to do that pre-training process. And the money that goes into taking a checkpoint for a model and training it up further, just by updating it, can cost potentially millions of dollars in a supercluster being ran by one of these organizations or rented out from a data center by one of these organizations trying to pre-train a model from scratch. So as a result of all of these different consequences, long term, there is a clear disincentive for these organizations to release pre-trained models as time goes on. There are immediate short-term and medium-term benefits that are obvious for releasing pre-trained models because it helps to set a certain standard around your architecture and your infrastructure that companies like Meta have been leveraging in order to catch up in the LLM AI sort of race that we're all kind of in right now. But unfortunately, it's not the same as open sourcing a piece of software. Like, for example, if you want to update PyTorch, it's just a few code line changes in certain cases, versus an LLM. You have to go through a very expensive pre-training process that costs a lot of money that eventually these organizations will probably want to cut down on as the costs increase through scaling their superclusters and compute and training processes, in addition to the potential threat that these models might pose to the wider world in terms of their capability and what they're able to accomplish. So right now we're in a very good situation where we're getting these pre-trained models essentially for free, but at a certain point, that's not something that the open source community can rely upon in the long term. And we have to be cognizant of that, which is why these different decentralized pre-training LLM alternatives are under consideration, despite being, in my opinion, in a relatively nascent stage. And I'll explain why and why I see that being the case as of right now. But let's just scroll back up a bit here. Let me actually make sure we're decentralizing and the problems. We've already specified those more or less. So yeah, let's get back up to the top. So ultimately, we need scale because it kind of goes back into this broader question of the bitter lesson by Richard Sutton. Great read. I recommend everybody into AI reads it at least once, especially if you're in a graduate program, because ultimately it dictates, or it implies that we get better performance from pure scaling, and from that we can gain collect emergent properties. But right now, the problem that we have with the scaling process that is outlined is that most data remains under private entities and control. Because with regards to scaling, of course, we need compute, but we also need significant amounts of high quality data that are likely going, and those demands are likely going to increase based on the current transformer network architecture that we use to actually create these large language models, because they're so data hungry in terms of the training process. We need more and more high quality data to train larger, better models. Now, to a certain extent, there's been an exploitation of data on the internet, and a lot of people are saying that, well, we're running out of data, we're running out of data resources or high quality data. And this paper acknowledges that too, where most of the world's data sources are unevenly distributed among private actors who often don't want to share it. And later in the paper, they do also highlight that we're running low on data, which I don't necessarily agree with. Like if we scroll down a bit further here, high quality public language data is liable for exhaustion within the next decade, while low quality language data may be exhausted in a few decades, which is a possibility, but is not something I think that is entirely mitigatable. For example, a lot of the data we have been covering and a lot of the data that has been used for language modeling has been from what can be considered the surface web. But as we all understand, or as I hope we all understand, the surface web, where we have these websites that are found through Google and web crawling, can only really be only really ultimately a small portion of the entire internet. Now, we have a lot of the deep web and the dark web in addition to that, which makes up a significant portion of the internet, a much larger significant portion of the internet, which includes, in the deep web case, cloud storage, patented data, research articles, legal documents, financial records. And all of this is very much centralized among data-rich private actors. So you have compute-rich, GPU-rich individuals and organizations, but you also have data-rich organizations and individuals who are not, and there aren't a lot of overlaps between both of those groups for a variety of different reasons, not all of them necessarily being legal. So in some cases, it's just a lack of desire to share certain private information as opposed to a lack of legal allowance. So as a result, we're not really scratching as much of the iceberg as we might assume from a lot of the language modeling data that we've recently been able to acquire in a public capacity. So I don't think the paper fully acknowledges the efforts that have been going into addressing the scaling issues that come from data, but that's a relatively minor critique given what they're trying to accomplish here. So some of the bigger takeaways from this paper, in addition to that, include that ultimately they are the first to succeed in generative pre-training of a billion scale plus model in a heterogeneous federated setting. Now, the reason why this is a big deal is because the concept of sharding and data parallelizing, these aren't brand new concepts. In fact, these were introduced back in 2001 by Meta. This concept of fully sharded data parallel training for faster AI training with fewer GPUs and for less communication overhead. So this is a concept that has been known about for years now and is part of what Flower Labs, one of the organizations who participated in writing out this paper, is leveraging in their distributed pre-training process for LLMs. The reason why this is a big deal in the case of this paper is that they're applying this in a federated, heterogeneous capacity. So the resources that they're being used to train the model are both heterogeneous and federated or decentralized between different nodes, which isn't really something that we've seen with applying this sharding technique. Usually it's done in a more centralized data center supercluster capacity. But in addition to that, it's managed to successfully train a model with over a billion parameters, in addition to several models that are below a billion parameters that they also highlight in the evaluations of this paper. So I just wanted to point out that the big takeaways really are that we're seeing significant development in a decentralized open source capacity for pre-training LLMs for people who might have a lot of data, but maybe not as much compute, which we see a lot more in, say, academic settings, private institutions or corporations. Bloomberg GPT was a good example where they had like a lot of really useful financial data, and they use that and a bunch of money to train up their own Bloomberg GPT. But it was very much a special case where they were able to leverage their private data and had the capital to invest in the compute resources necessary to train their own in-house LLM. So as a result of those financial and data-rich benefits, they were able to leverage their data to create an LLM or to pre-train an LLM from scratch. But again, most data-rich organizations and individuals don't necessarily have that data compute rich environment to leverage their data, or their that GPU rich environment to leverage their data in pre-training a model from scratch, and nor would they necessarily want to risk sharing that data in the process of pre-training a model from scratch, which is where this sort of federated learning process comes in. So the organization responsible for this paper, it's a collaborative effort between the University of Cambridge's Department of Computer Science and Technology and this organization known as Flower Labs. Now, Flower Labs has a GitHub, and they are using this Flower framework for federated learning. This is mentioned in the paper as the framework that they were updating in order to continue leveraging this framework to build out LLMs above a billion parameters in a federated capacity. So I would keep an eye on this repo in particular, as well as their website. They have a blog in addition to that with a bunch of different documentation. Some of the people who actually wrote this paper or participated in creating this paper actually do write blog posts on the Flower AI blog. I believe one of them was Nicholas Lane. He was mentioned at the towards the top of this paper. Yeah, towards the bottom of the paper here, which means that in general, the people at the top are usually the ones doing the most work, but the people at the bottom are usually the most senior in any given paper. So Nicholas D. Lane is one of the more senior people participating here, in addition to all of the individual researchers working on the efforts for creating this paper and writing up the paper itself. So just a little bit more context that I think is kind of relevant in appreciating this, on its own terms. But with that sort of background on Flower Labs as an organization, given that they've also been working on this sort of federated learning and this sort of framework for doing federated learning for roughly the same amount of time that has gone by, so about since like 2020, 2021 at least for that framework specifically, which is roughly on par with when Meta introduced the fully sharded data parallelism. So as we can see, one of the earliest contributions are about 3 years ago. 4 years ago for the initial license commit. So roughly about 4 years for that framework, which is roughly about the same amount of time it took for the fully sharding introduction for Meta. Anyways, just thought that helps to kind of explain where all of this is coming from. This sort of technology and development has been an iterative, long time effort over the last few years, and is something that is likely going to continue to become more and more relevant as we start seeing capital expenses for training up and pre-training up models going higher, and less organizations feeling inclined to share those models for free in an open weight capacity on, say, Hugging Face. All right. So with that all being said, continuing on the paper, a lot of their efforts were accomplished through interlinking single nodes containing roughly 1 to 8 GPUs from standard cloud providers. So one of the critiques I do have about this paper as well is that they're using rented GPUs from cloud providers. So we're seeing a lot of A40s, A100s, H100s. If we actually look in the document a little bit later as well, we kind of see this mentioned, that it's a heterogeneous set of servers equipped with NVIDIA A40s, A100s, H100s as GPUs, which are not really commercial grade GPUs. I would like to see nodes that consist primarily of more commercial grade GPUs, like maybe 3080s, 4080s, 4090s, stuff like that. Like those RTX NVIDIA GPUs would be pretty interesting to see it within these nodes and how they perform as well. More of a minor critique. It really shouldn't affect the results, but something that came up as well while I was reading through the paper. But in addition to that, going back up here where we were at, we also had these larger, we also found one of the bigger takeaways that these larger federated LLMs find consensus across these different clients or nodes more easily than smaller versions. So which that roughly means that as we have these models scaling up more with these different nodes that share resources, the training process actually becomes more stable, which is counterintuitive relative to a centralized data center. Normally, if you're scaling things up further and further in a more centralized data center with more than one supercluster, training can actually become less stable due to the communication overhead. So the networking really becomes a big bottleneck in training between data center superclusters, because you really can't afford any latency or packet loss in the training of these models and updating the gradients associated with training these models. But what ends up happening with this sort of federated learning process is that you can avoid a lot of that communication overhead, because there's less frequent communication. There's less of a need to share gradients all at once and to synchronize the sharing of those gradients because of the way in which federated learning works. So under their system, large models require less frequent communication while receiving a greater boost in generalization performance than smaller ones. So as the models scale up under this federated learning paradigm, there is more general stability and a greater level of generalization across the data set through the way in which they aggregate these gradients or these generalizations within the model. And ultimately, by leveraging their execution engine, they're able to balance loads across these different computational nodes, which allows them to establish a training pipeline that is ultimately faster and more robust than its centralized counterpart through those same processes I briefly covered. Now, I'll go into a bit more depth as we continue into the paper, but I just wanted to mention that primarily for context, this sort of fully sharded data parallelism, or this there's different types of parallelism in training up large language models. And generally, LLM pre-training is based primarily on 2 denoising pillars that they cover here. So leveraging huge batch sizes or training rounds with large quantities of different examples for the model to kind of just take in, and very long context. So very long sequences of data that are all getting trained within a sequence length of a single input sample. So, and this denoising process is essentially the way in which these models end up getting more of a signal towards training in a way that is generalized. So they're trying to find the local minima or the global minima, ideally. And as the gradient descent is occurring or going down to that minima, there's a lot of noise that can shake that out, depending on your optimizer, depending on a variety of different factors. But ultimately, the pre-training efforts boil down to those batch sizes and that long context. And there are different ways of parallelizing this training in order to take the load off of a single GPU, because you ultimately can't train models these large on a single GPU, or at least it's very difficult to try and train something even close to this large on a single GPU, although efforts are probably being made as we speak to try and do that. But largely, we rely on data and model parallelism. And the bigger differences between data model parallelism that show up here in this paper, if I look in my notes, I wrote kind of more about the differences here, or these different types of parallelization. Let's see here. There it is. Okay, so for model parallelism, ultimately the model's parameters are split across multiple GPUs, and then each GPU is ultimately responsible for a different subset of the model's parameters and computes only part of the forward and backward passes in the training process, or the gradient descent training process for these different models. But we also have data parallelism. And with data parallelism, the entire model is replicated across the GPUs. So the whole model itself is essentially copied onto each of the GPUs, and each GPU processes different batches of data independently. So from there, the gradients are then averaged across all the GPUs to update the model. And the problem is all of the calculations that go into each of these gradients they create a lot of communication overhead, which is why we start to see something like fully sharded data parallelism, which kind of gets the best of both worlds from both model and data parallelism, which is what this paper is doing in a federated capacity. So in fully sharded data parallelism, as was covered in Meta's introduction of the concept, this approach combines elements of both model and data parallelism. So you get to shard or split up the model between different GPUs, in addition to splitting up the forward and backward computations as well for these smaller versions of the model that are then aggregated together into the global model that ends up getting created through this federated learning process. And again, the key thing here is not that they accomplished fully sharded data parallelism as much as they did it in a federated learning capacity. So a distributed capacity, you could be in potentially different countries or in different buildings or in different cities, aggregating this compute process through these nodes. And they talk about this process in sort of a client server phrasing, which I think a lot of you coming in from software engineering and development backgrounds will be able to appreciate. And it's something that I personally found helpful in understanding this paper. But that being said, we already kind of covered the high quality public data set being liable for exhaustion. And again, I don't really think that we're circumventing either the costs. I don't think these are the only solutions in the paper for the different bottlenecks they outline. I think they're not considering things such as leveraging more beyond just the surface web that we've covered earlier, that 5% we already have access to. And I do think organizations like Meta, given the amount of data they have from their different social media platforms, might start to leverage that information in their training process if they haven't already. But just these are things that we have to consider that haven't been necessarily included here. The effectiveness of synthetic data generation has gotten a lot better, and you really, for the most part, based on the Orca paper released by Microsoft, only really need a large quantity of high quality data, which you can get through synthetic generation means. You can actually get better high quality synthetic data in some cases that you can then leverage to train better models. And well, we do also want significant data efficiency improvements and general optimizations of these different architectures. Attention is just really good as a mechanism, and I don't think we're going to fully get away from it as much as we're going to try and do our best to make it as efficient and scalable as possible. Again, going back to the importance of architecture only being that it is able to scale more efficiently and effectively in getting these models to be larger and larger. So with that all being said, we have this problem of accelerators also needing to be largely uniform in specification to avoid stragglers or latency or packet loss in these larger centralized data centers, that in addition to needing to be extremely well connected to avoid a lot of these networking problems and these communication bandwidth that comes in from um, a centralized sort of data center or set of superclusters trying to pre-train a model in a centralized capacity. And there's different synchronization requirements for being data parallel or through fully shared data parallel, stochastic gradient descent. And ultimately, these are the big constraints that this sort of federated learning process is trying to get around through leveraging these similar ideas for fully sharding data parallelism between these different nodes. So we already covered that. This might be a spelling error. I think they meant comply instead of compile, to comply with privacy regulations instead of compile with. Sometimes they're weird spelling errors like that. The former English major in me likes to double check those. Now, again, this is kind of another section where they highlight, oh, we're already able to do federated fine tuning and parameter efficient fine tuning of LLMs, which again isn't really a big issue in my opinion. If we have LoRa's or QLoRa's, or it's great that we can use federated learning to do fine tuning already, and that is kind of a solved problem. But they just kind of highlight that as well as one of the benefits of federated learning, that you can also use it for fine tuning. I'm just going to gloss over that because that isn't really the bigger takeaway in my opinion from this paper. And we additionally have design principles for federated generative pre-training of LLMs. So we have these different federated LLMs for, these different design principles for federated generative pre-training of LLMs. Just getting a quick alert here. There we go. And we ultimately get a lot of benefits, like a broad access to more data-rich environments, individuals, and organizations. So the way this ends up working out is that because you're only sending the calculations from these different nodes back to a sort of global server that then aggregates those calculations for these parameters into a single global model, like a single large model, you're not actually sending any of the data. It's all being kept locally within your own environment for these different local gradients that you're updating each round, and you're doing multiple rounds of updating the set of parameters that then get aggregated into this larger global server that then creates this LLM from these different parameters that are trained locally on your data. And that's how they end up doing this sort of federated and sharded process. They split up the model, they train up the model locally, multiple rounds for that split up portion, and then they send it back to be aggregated based on the parameters, not the gradients, because the gradient calculations are really where you end up getting the most communication overhead in pre-training these models, and is one of the problems that you end up seeing with the networking issues that go into using either Ethernet or InfiniBand in training models in a centralized data center with a bunch of superclusters, which is something that Meta has also highlighted and has worked to address on their end in the past. That's a whole other discussion, though. But ultimately, you address the limited communication requirements, which is training should be possible without any strong synchronization requirements or standard data parallel training, where you don't need to have that entire model being replicated across GPUs and each of the GPUs processing the data independently with that information needing to all essentially be pooled in the same location. So you shouldn't need to have to worry about that. You want broad hardware inclusivity, so different GPUs and a heterogeneous setup, that sort of thing, and then scalable local training pipelines. So a federated training system ultimately you want it to be effective across a wide range of model sizes, and building systems for supporting local training pipelines for these different scales, whether it's above a billion sized models or smaller models. You want that fully sharded data parallelism to do simple data parallel training and CPU offloading as it is required for any given pre-training of an LLM. So ultimately, some of the big takeaways they got from their experiments, for context, they used a version of C4 or the Common Crawl data set, which is essentially just an English data set that's about 750 to 800, about 800 gigs of data. And it's entirely in English, and it's a relatively standardized, like pretty, well-established data set at this point, but it's not. Again, that's one of the things that I'm going to point out as a particular issue, because ultimately, and this is something they acknowledge in the paper as well. So we'll actually get to that a bit later. But they use C4 and they train up these different size models, 75, 125, 350, and 3.5 billion for these different rounds. And as you can see, they do scale up the batch size with 1.3 billion. But as a result of this, they notice that with their same resources, larger models improve consensus, which means that the stability of the training procedure ultimately improves directly with the model size. So as models get bigger, the training procedure gets more stable, as opposed to having a lot more weird jumps in, say, perplexity, for example, which is highlighted in these different graphs here. So these are the smaller models. Specifically, I believe this is the 275 and this is the 125. This is the 350. But as you can see with the larger models, we start to see more and more stability in the drop of perplexity from these models or confusion in output, as opposed to like a bunch of jumpiness here and there that doesn't have a smooth level out. You generally want more of a smooth level out in perplexity rather than random spikes in said perplexity during the training process. So that tends to stabilize. Additionally, there's an interplay and alignment between these different node clients and the server that aggregates them. So they become more and more similar to each other as the training goes on, and there tends to be a sort of consensus between the two. And additionally, there also tends to be a more of an alignment as well. So there's a general convergence that can be observed between these different clients and this global server, which is updated through a sort of pseudo gradient. So the different calculations for these different local gradient calculations end up getting essentially aggregated into a sort of pseudo gradient that gets updated for the global server, which is just kind of an approximation of a gradient you would normally have updated for a pre-trained large language model if you were to do it in a more centralized, non-federated capacity, right? So ultimately, those are the big takeaways from this paper. There's still a lot of work to do that they highlight. One of the big things they mention here is that the C4 paperwork is not something where they used a lot of different languages or genres, but that's something that they want to focus more work on in the future. They additionally want to fine-tune these models on different established benchmark tasks to assess performance based on the different LLM benchmarks that we commonly see, probably something like HelloSwag, MMLU, GPQA, stuff like that, where you use those different benchmarks to kind of see if these models are actually like good at these different benchmark tasks. I think they probably could have done this within the same paper as well, but probably just getting something like this to work in the first place beyond a certain threshold is decent enough work for a single paper, and it doesn't kind of over bloat the paper because it kind of keeps things relatively concise, which I can appreciate personally as somebody having to read a lot of these where it's just page after page of like AI generated text that does kind of just re-loops itself over and over again without really getting to a point. There's a lot of that, and I don't really see as much of that type of stuff in this paper, if any of it. So that was nice. But ultimately, they also are going to be scaling up this federated setting. So basically, they want to create bigger billion-plus models and ideally use more heterogeneous data sources and software because, again, C4 as a data set, the Common Crawl data set is relatively uniform in how it's formatted, relatively uniform in how it's formatted. And it's primarily in English, if not entirely in English, if I remember correctly. But they want more languages, more genres, probably more data formats, and generally a broader participation in federated learning, which is why one of the reasons why I wanted to share this framework with you all. So if any of you are really interested in federated learning or decentralized LLM pre-training, you definitely want to check out flower.ai. You want to look at some of their GitHub repos, particularly the Flower framework they have here for federated learning. I do think they're going to be updating that as it relates to the findings from this paper. They do plan to release all of the information associated with this paper. As of right now, I don't believe this open source framework has these updates publicly available in it, but I could be wrong. You may want to check the most recent updates for it. So with that all being said, there is a lot of context that I think is relevant for understanding this paper. And I think there are some good takeaways, but based on what we've already covered, there's still a lot of things that can be done in the relatively nascent stages of developing decentralized pre-training for these different LLM models. We're still very much in the early stages. We haven't really kind of gotten this to scale more or cover more varied data sets in ways that I would personally feel comfortable with if we were to need a full replacement from, say, a model pre-training company like Meta or Mistral or what have you. So it's not fully there yet for that sort of drop-in replacement, but it is something that can kind of be kept on in the back pocket of the open source community to leverage if pre-training ever ultimately, like, pre-trained models are no longer being released by these larger organizations, like if that wellspring ever dries up in a sense. So with that all being said, I think we've got a good amount of time for questions. Does anyone have any questions for what we've covered thus far? All right. San, I notice you have a hand raised.
Yes. Hi, Mike. How are you?
Oh, fine, thank you.
It's good to see you again. It's been a while,
Yeah,
and very
likewise.
happy to be here. For those who just joined, I'll give a very brief introduction. My name is Hassan. I'm working as a data scientist and ML researcher in Turkey in a manufacturing company. So, having said that, um, I wanted to ask for the evaluation part. I
Mhm,
couldn't quite get the insight from the last graph, where
mhm.
we were drawing a parallel between federated versus client gradients. Maybe you could highlight it a bit more.
Oh, yeah, absolutely. So let me actually go back to the document here itself. So the last graph was the federated optimization aligning client gradients, right? This one?
Yes.
Okay. So the cause of client model convergence can be observed in Figure 4, which showcases the relationship between the norms of the per round pseudo gradient, i.e. the average client update, and the local client gradients applied at every stochastic gradient descent step. While the pseudo gradient starts much larger than the applied local gradients, it reaches a similar work or much smaller size as the client model converges. So what I think this figure is trying to highlight about the federated optimization, it's that, so you have the local client gradients or the gradients within the nodes, and then you have this sort of pseudo gradient that gets updated in by the global server, was my understanding. So what they're trying to highlight here is that there's not really as much convergence between these two gradients, both the local client gradients and the pseudo gradient. But like with the client and server, uh, or the client and server, like, global model, there's a convergence. They're just highlighting another convergence between the different gradients as well. Does that make sense?
It does. It does. Thank you. Thank you very much.
Yeah, you're very welcome. All right. Any other questions? You all can feel free to just talk as well, by the way. I don't mind. Like, you don't need to raise a hand. If you just want to open a mic and start chatting, I'm fine with that too. All right. So if there are no further questions, or if people don't want to ask any questions on the recording, I'm going to stop the recording now. And I hope you all have a wonderful rest of your day. If you don't have any further questions, take care, everybody.